And here we are again. So welcome back to Cosmology, part 46 of 87, I think. We're talking about the cosmic microwave background, and we're interested in understanding the time or the temperature at which the universe goes from opaque to transparent. And in order to figure that out, what we really need to learn about is when the number density of ions, when the plasma in the early universe goes from being, well, a plasma to just sort of a gas of neutral hydrogen. So we're working towards getting this fractional ionization, X, as a function of temperature. The last thing we have discussed was this derivation of the so-called Saha equation. And before we get into ultimately getting the fractional ionization, I just wanted to give a very brief introduction to particle physics units, for those of you that have not seen this. And I wanted to just sort of indicate how it is that one can figure this out. So just I guess a brief aside about units. Particle physics units. So it's oftentimes the case that when you're thinking about particle physics, one will let h bar be equal to 1, c be equal to 1, and then also the Boltzmann constant be equal to 1. Okay, that just simply means that, at least for the moment, you imagine working in units that aren't SI units like kilograms, meters, and seconds, but some other set of units for mass, length, and time in those units. These constants have those values, and also the Boltzmann's constant being equal to 1 just means you've chosen your units for temperature to be such that that's true. If you do that, then it turns out that the units for various things, so what we'll have is length and time, and I'll just sort of indicate that with an L, a lowercase t, right, mass, m, energy, E. I want to show you that many of these quantities can be simply related. At least they all, on some level, have can be put in a form where they have the same units. What I'm trying to get at is that when you let these things be equal to 1, then if you have an inverse length scale, that is to say 1 over L, that should have the same units as 1 over time. There we go. And that has the same units, I claim, as units of mass. That has the same units as energy. And that has the same units as temperature. There are other ways to write this, but for example, if we want to have everything, let's think about things in terms of energy units, then clearly energy units have units of energy, so this one's already ready to go, this one here. To convert a unit of mass to unit of energy, what you would do is recognize that the only way that this could possibly be true, that the units of mass are equal to units of energy, is if there's a missing factor of c squared. You know that mc squared, Einstein's famous equation, that c squared should really be there, but if c is equal to 1, that's why you get to drop it. If you have units of 1 over time, or frequency, for example, you know that Planck's famous equation, energy of what turned out to be photons, is equal to Planck's constant times frequency. Planck's constant h has the same units as h bar. They only differ by a factor of 2 pi. And so there should be a secret factor of, well, if you like, h bar over here. And if it's set equal to 1, then basically you don't see it. Likewise, a factor of h bar times c will do that as well. And then what's missing here is a factor of k Boltzmann. So I guess what I'm trying to say is that if you want to think about whether quantities have the right units, then if you allow yourself for a moment to at least ignore factors of c and h bar and Boltzmann's constant, then you can hopefully quickly identify that as being the case. What that allows me to do, for example, when I look up at this equation and I see a number density divided by a number density times a number density, what that tells me is that this whole thing has units of 1 over number density, and number density has units of inverse length cubed. That means 1 over the number density should have units of length cubed. So I would claim that the left-hand side of the Saha equation has the units of length cubed. On the right-hand side, we've got something in parentheses to the minus 3/2 times an exponential. Well, that exponential, we know that by itself should be unitless. In fact, we've got units of energy on top, units of energy on the bottom, so don't worry about that. Then the question is, what are the units of this thing on the top? So let's just perhaps isolate, let's try anyway, to lasso this, and just see if we can convince ourselves that this quantity has units of length cubed, and then we'll move on to perhaps more interesting things. When I see this m, and so let me go ahead and do something. Let me just point out the things that I want you to ignore. Factors of 2 and pi have no units, so let's just ignore this. And I want you to imagine that we're working in units where the Boltzmann constant and h bar are equal to 1, so we'll ignore all of these terms. And so really what you've got here is something that looks like me times temperature all raised to the power of minus 3/2. But if we go back and we look back at what I had claimed, that units of mass have the same as units of, let's say, energy, and units of temperature have the same as units of energy. So if I just wanted to ask what are the units for this thing here, it would have the same units as this, and a mass has units of energy, temperature has units of energy. So this has units of energy squared all raised to the power of minus 3/2, and an E squared to the minus 3/2 power, the units thereof rather. This should have units of energy to the minus 3. And the units of energy have the same, apparently. If we go back to what's in green here, you'll notice that, I can write this as units of energy are the same as units of inverse length. And feel free to stick in h bars and c's wherever appropriate. For example, if you wanted to make this true, you would stick in an h bar c there in the end. Or what that means is that the units of energy divided by h bar and c give you units of inverse length. The point is, these units of energy to the minus 3 should have the same as units of length to the positive 3. And there you go. You've convinced yourself that it has the right units. All right, so we're interested in getting the fractional energy as a function of temperature. In other words, we're trying to get x of t. Given the Saha equation, which I had written up above, that is to say the number density of hydrogens over the number density of protons, number density of electrons, and can I go off of memory? Oh, here, it's written down here, good. This is approximately equal to the mass of the electron, Boltzmann times temperature, divided by 2 pi h bar squared. I guess this is raised to the minus 3/2 power. And then e to the q over kBt. Again, q is the binding energy of hydrogen, and that's roughly 13.6 electron volts. Now, the definition. So we're going to need to use 3 equations in order to figure out what is the fractional ionization. For one thing, let's call this equation number 1. This fractional ionization was defined as the number density of protons divided by the number density of baryons, right? This is the number density of loose protons. The number density of baryons, right? Where are all the protons? They're either free or they're in a hydrogen atom. So we can write this as Np over the number density of protons plus the number density of hydrogen. And then lastly, because we are assuming that they're the only kind of atomic elements there are out there, the only kind of atomic constituents are protons, electrons, and then bound hydrogen atoms. What that means is the number of protons should be equal to the number of electrons, talking about the number of free electrons here. So feel free to write it that way. We should also keep in mind that we had thought about, or we had defined this baryon to photon ratio, which is called eta, and that was simply the number density of baryons divided by the number density of photons. Okay, so I'm going to box these things because we're going to need them. And the third equation is just a fact, something that you can look up in Ryden chapter 2, but in more convenient units. The number density of photons, right? This is determined by statistical mechanics and is proportional to the cube of the temperature. This turns out to be equal to a number that you can write down, 0.2436. That should be, I hope I get this right, that should be per cubic meter, and then times the Boltzmann constant oh no, this is all the units we need are already right here. This is Boltzmann's constant times temperature divided by h bar c divided by cube. I know that, by the way, because kBt has units of energy, whereas h bar c has units of energy times length. And so this whole factor here then has units of inverse length cubed, and that's what the units for number density should have. Okay. These three equations should be enough to get us going. From equation 1, what I want to do is solve for the ratio of number density of hydrogens to number density of protons. So from 1, flip that equation around and verify this in your notes, would you please? This is equal to number density of protons, number density of hydrogen divided by number density of protons. This is 1 plus NH over NP. And I just want to focus on solving for this right there. What you can hopefully see quite easily is that if you solve for this ratio, NH over NP, this should be 1 minus x divided by x when you find a common denominator. Okay, so that's something that we're going to use. So let's just kind of underline that. If you also, from equation 1 and equation 2, what you can do is solve for the number density of electrons. That should be given by, well, it's the same as the fractional ionization times the number density of baryons. But I will replace the number density of baryons with eta times the number density of photons. In other words, the number density of electrons is equal to x times eta times number density of photons. Okay, good. That being said, we are ready now to shove this into the Saha equation, right, which has NH over NP divided by NE. So into Saha. Saha was a person, by the way. It's not just a fun name. I mean, it is a fun name, but it wasn't invented. Anyway, this is equal to this first part, 1 minus x over x, divided by this thing that we just found. In other words, 1 over x eta and the number density of photons. And all that's equal to the right-hand side of Saha, which, in other words, this should be equal to mass of electron, Kb times T, divided by 2 pi h bar squared, and all raised to the power of minus 3/2. And don't forget that exponential piece. Okay. We would like to be able to solve for x. And so let's try to get all the x-related stuff on the left-hand side. We're basically there. We've got a 1 minus x over x squared, and then take that other junk over. In other words, let this be equal to eta times the number density of photons times this thing in parentheses to the minus 3/2 times e to the q over kBt. Now, the last step will be to use what we had written down before, which was somewhere up here. Yes. We need to use this equation now to replace that number density of photons with some numerical factor times kBt over h bar c cubed. There's some cleaning up you have to do. I think it's definitely worth you going through and verifying that this is approximately equal to 3.84. I verified the number too. I did my homework, I promise. This is multiplied by the baryon to photon ratio eta, and then what remains is, in parentheses, kBt divided by mass of electron c squared. So the top and bottom have units of energy, and they therefore cancel. This is all raised to the power of positive 3/2, and then there's an e to the q over kBt. Okay, that is an equation that relates your fractional ionization to, well, temperature and mass of electron and electron binding energy. The last thing to do is just, well, a little bit of algebra. So let's let this whole right-hand side define this to be the parameter s. Then you can solve for x. Then it would turn out to be the case that s times x squared, right, plus x minus 1 is all equal to 0. And then you can solve for x. You would find that x has to, of course, what is it? Negative b plus or minus the square root of b squared, or 1, minus 4 times a times c, which is a minus 1, which makes this a plus, all over 2a. Now the thing is you have a plus or minus solution. You got to realize the math doesn't distinguish between the two, but because we know the range on x, the physical range has to be between 0 and 1, that means very clearly we have to choose the positive solution. Okay, the negative solution would give you numbers that were, well, less than or equal to 1, so that's no good. So there you go. That is the solution for x as a function of temperature. So I'll sort of indicate that. This is x as a function of temperature, and the temperature dependence shows up in this parameter s, right? S is a function of temperature as well, which is defined like so. Lastly, it's not like there's a one critical moment when the universe goes from being an ionized plasma to being neutral, but we can let what I'll put in quotes recombination be when s is equal to 1/2, which is to say that, right, half of the protons are in neutral hydrogen atoms and half of them are freely flying around. This is good enough to get at least a sense of scale. Get the scale. That is to say, really what we're interested in the sort of temperature at which recombination occurs. More details to follow.